This session is all about definitions. What does it mean to be an acid and base? What are some words we use associated with acid-base chemistry? What do we mean by strength? And what is pH? So there's more than one way that we can define an acid and a base. The first one is the Arrhenius definition. Same guy as the Arrhenius equation. He worked on a lot of different things. He's actually a little bit more famous for this stuff. And so in an Arrhenius acid, an acid dissociates to release H+. So for example, you could imagine that HCl dissociates to form H+ and Cl-. And so that makes HCl an Arrhenius acid. An Arrhenius base is something that dissociates to produce OH-. So for example, NaOH can form Na+ and OH-. So this is one definition of an acid and a base, but it doesn't really cover all the possibilities. So people kept talking about this idea of acid and base, and another definition that we came up with that is more general and therefore more useful is that an acid donates a proton and that a base accepts a proton. So instead of defining acid and base in the Arrhenius way by H+ and OH-, now we're talking about donating and accepting. So an example of a Bronsted-Lowry acid is still HCl. But in this case, we're going to imagine that HCl donates a proton to water to make H3O+ and Cl-. And so you'll see that when we're writing out acid and base reactions, we're always going to imagine that there's something for that proton to go to, right? It doesn't just leave, but it gets donated to something, and that something is usually the solvent, water. A base accepts H+. So in this case, we can think about how ammonia could be a base. Ammonia can't donate OH-, but it can accept an H+ from water to become NH4+. And then by accepting an H+ from water, it produces OH-. So you see, the Arrhenius concept and the Bronsted-Lowry concept, they're both getting at the same observations about acids and bases, but they do so in different ways. So for the most part, in Chem 132, we're going to use the Bronsted-Lowry model for how to define an acid and a base. Okay, so here's sort of another representation of the same thing. We see that in the equation that we just wrote, where ammonia acts as a base accepting a proton from water, that what that means is that water is the acid. It is the water is donating a proton. So in this figure, we can see that water loses a proton to become OH-, and the NH3 gains a proton to become NH4+. When we think about the relationship between water and OH- and between NH3 and NH4+, we call these conjugates, so that the conjugate only differs by a proton. And in each conjugate acid-base pair, one of them is the acid form that donates a proton, and one of them is the base form that accepts a proton. It doesn't really matter which one we call the base and which one we call the conjugate acid, or vice versa. The point is that they are conjugates of each other. And so we see that in an acid-base reaction, we start with an acid and a base, and we end up with a conjugate base and a conjugate acid. So here's some other definitions that will be useful for us as we're talking about acids and bases. A monoprotic acid loses one proton. So chemists often use the word proton to mean H+ ion, because if you think about it, a hydrogen atom has one proton and one electron. So if you remove the electron, all you have left is a proton. And so an example of a monoprotic acid is, once again, HCl, because when it reacts with water, it can lose exactly one proton to make H3O+ and Cl-. A diprotic acid can lose two protons. And we think about those happening in separate subsequent reactions. So for example, carbonic acid can react with water to form the conjugate base, hydrogen carbonate, and H3O plus. And then we see that HCO3 minus hydrogen carbonate, it still has a proton that it can lose. So we imagine it going through a second deprotonation to form carbonate ion and another equivalent of H3O plus. So carbonic acid would be an example of a diprotic acid. A polyprotic acid is just another word that means, in this case, more than one proton. And so a diprotic acid is an example of a polyprotic acid, but we could imagine triprotic acids or so on. An amphiprotic acid or base, or an amphoteric species, is something that can be either an acid or a base. And so actually, that hydrogen carbonate ion is a good example. It can either accept a proton from water to form carbonic acid again, and OH minus, so here it can act as a base, or it can act as an acid by that second reaction we looked at before, where hydrogen carbonate reacts with water to form carbonate and H3O plus. So which one does it do? If it can be an acid or a base, which does it choose? Really, it does both, but it might not do them in the same amounts. So now we need to define this idea of acid strength. So the strength of an acid is the extent to which it ionizes when dissolved in water. So we've been drawing these reactions where some acid, so here's a generic acid where we have HA, so this is our generic acid, and its generic conjugate base. Okay, where we have that HA reacts with water to become H3O plus and A minus, and we see that we've drawn equilibrium arrows because this reaction is potentially reversible. And we know that it will go toward equilibrium, but that equilibrium could be really close to the products or really close to the reactants. The closer the equilibrium is toward the products, the stronger the acid. Okay. So we can think about what that looks like on the molecular level. If we started with a solution of a strong acid we would expect basically 100% dissociation, where it all becomes H3O plus and the conjugate acid. Okay, so we'd start with HA, we'd get stoichiometric amounts of H3O plus and A minus, the conjugate base, after the reaction. And so if we were to use our microscope to look down at the solution, we would see at equilibrium that we have conjugate base molecules that are shown in yellow, and we have H3O plus molecules, and that would be it. A weak acid only dissociates partially. So we still have some HA, some of the reactant, left over at equilibrium, as well as some H3O plus and A minus. So if you were to zoom in on the solution at equilibrium, you would see that we have some conjugate base and H3O plus, but we also have a significant amount of the HA acid form. So if the extent of dissociation is rather less than 100%, that's what we call a weak acid. And we can imagine that being, sort of on a spectrum where we can even have a very weak acid, where basically none of the HA dissociates, and so we have no H3O plus or A minus at equilibrium. And so these represent a spectrum. We can have things that are strong-ish and things that are weak-ish and everything in between. In general, as a general principle, the stronger the acid at being an acid, the stronger the acid at donating a proton, the weaker its conjugate base will be at accepting a proton. And vice versa, a weaker acid will have a stronger conjugate base. So usually either the acid form is better at being an acid or the base form is better at being a base. And we can, once again, think about that in terms of equilibrium, and that the equilibrium is either going to be more toward the reactants or more toward the products. And so if it's more toward the reactants, that means that we have a weaker acid. And so if we put the base into solution, that base will be better at reacting with, so maybe if we had a weaker acid, the base would be better at being a base. Some acids and bases dissociate so completely that we just call them strong acids and bases. The number of strong acids and bases that can be considered to dissociate 100% is small enough that we just memorize them and identify them. Everything else that isn't a strong acid or a base, we consider those to be weak acids. So here are the 6 strong acids and the 6 strong bases I want you to memorize, and you can find this table in your textbook. Water can be both an acid and a base. Water is also amphoteric. And so we see here water acting as a base when it donates a proton to the other water molecule. And it can also be a base when it accepts that proton from another water molecule. We call this the autoionization of water. And we can represent the equilibrium here using this equilibrium constant expression. So we see that we have products over reactants. So we've got H3O plus and OH minus, each raised to the first power. But we don't have liquid water on the bottom because it's a pure liquid. So this equilibrium constant expression is so special. We use it so frequently that we give it a special subscript, Kw. So whenever you see Kw, you know that that refers to this reaction where we have water molecules becoming H3O plus and OH minus. So that is always Kw. And we also know that the value of Kw at 25 degrees C is equal to 1 times 10 to the minus 14. And so if we think about what that means for our reaction, it doesn't really matter how much water we start with because water is a pure liquid. But if we were to draw out something like an ice table here, that if this mixture is going to go to equilibrium, if we start out with no H3O plus or OH minus, and we know that we're going to make some, then we know that at equilibrium, in pure water, we're going to have equal amounts of H3O plus and OH minus. And so if we put our x squared into our equilibrium constant expression and solve for x, we see that the equilibrium concentration of H3O plus in pure water is 1 times 10 to the minus 7 molar, and that will be equal to 1 times 10 to the minus 7 molar OH minus. And so we define that combination where we have 1 times 10 to the minus 7 molar of each of the H3O plus and OH minus, that is a neutral solution. If our solution has more H3O plus because we've added H3O plus from some other source, then it would be acidic. If the solution has more OH minus, it would be basic. But in any case, at equilibrium, the product of H3O plus and OH minus will always produce 1 times 10 to the minus 14 at 25 degrees C. So try this one. What is the OH concentration of a solution that contains 2.59 times 10 to the minus 4th molar H3O plus? Okay, so we want to find the OH minus concentration. We know that this is just water, so Kw is going to equal OH minus times H3O plus, or the other way. And if we want to solve for OH minus, then we divide both sides by H3O plus, and we get that OH minus equals Kw divided by H3O plus. At 25 degrees C, Kw equals 1 times 10 to the minus 14, and the H3O plus concentration of our solution is 2.59 times 10 to the minus 4. And so if we solve for the OH minus concentration, we find that at equilibrium, the solution would have 3.86 times 10 to the minus 11th molar OH minus. So you see, if we know the concentration of OH minus or H3O plus in solution, we can find the other one using Kw. Another way that we can represent the OH minus or H3O plus concentration, really the H3O plus concentration in our solution, is by pH. You saw in the previous slide that our number was 3.86 times 10 to the minus 11. It's a little bit hard to carry around that scientific notation. So instead, we calculate pH by taking the negative log of the H3O plus concentration. And the point of that is that the negative log part helps us to focus on the exponent. So look here. If you have 1 times 10 to the minus third molar H3O plus, then that is going to give you a pH of 3. So we know that the concentrations are usually 10 to the negative something power, and so we use the negative to make the pH a positive value, and so we see that the exponent matches the pH. If we use kW to find OH minus, we'll see that the OH minus concentration would be 10 to the negative 11, and we could also do negative log of OH concentration to get pOH. And we see that that matches the exponent there. Same deal in neutral water, where we have 1 times 10 to the minus 7 and 1 times 10 to the minus 7 of each. That means that our pH is 7. So you're probably used to the idea of pH 7 being a neutral solution. Same deal if the numbers aren't 1. So if we have 2 times 10 to the minus 9, we can see that that will give us a pH that is close to 9, but a little bit less because we have a little bit more than 1 times 10 to the minus 9 molar H3O plus. So we have decided that solutions that have a pH less than 7, so more H3O plus than OH minus, we call those acidic. If we have more OH minus than H3O plus, we call those basic, and so that'll be pH between 7 and 14. Remember that you can always find the H3O plus and the OH minus using kW. The solution of the pH of a solution can vary, and we see that there are solutions that have all kinds of different pH values. You can see here that some of your foods like lime juice or vinegar, wine, orange juice, or coffee, those tend to be acidic. Things like your blood or ocean water or baking soda, milk of magnesia, like Mylanta, those tend to be basic. And so we can see solutions out and about in the wild that have all different ranges of pH.